and software together. So if you're familiar with Spark processors, we've introduced a number of processors over the years. Currently, we're shipping 2 processors, M7 and S7. They execute the Spark ISA, and what we introduced with them was software and silicon in the areas of security and in the areas of SQL acceleration for our database. And we've also worked with our Java teams and other teams that we can actually use the analytics acceleration for items outside the database. So that's what I'll specifically talk about today. As a background, our processor itself, and I'll just use M7 as an example, is a 32-core processor. Cores, are anyone familiar with multi-threaded processors? These are multi-threaded cores, 8 threads per core. On this block diagram on the right, you'll see there's a multi-level cache hierarchy, and the 3rd level cache there in gold is interesting from the standpoint that it's a shared cache, but it's partitioned to the point that it brings data that specific processor cores are using closer to those processors. So it's somewhat of a NUCA cache, and it allows us to migrate hot data to where it's needed. Another important thing about processor development, any type of processing, is being able to move information in and out of the processor. So one of the things we really focused on was memory bandwidth and I/O bandwidth. Anything to do with storage, anything to do with database in memory is how much information can you move in and out. So what we have is we have a up to 2 terabyte memory subsystem that supports over 170 gigabytes per second aggregate memory bandwidth, which is significantly higher than what you can find in most processors out there today. The thing I will address today is this notion of data analytics acceleration. So this is hardware specifically developed with our software teams. That's domain specific. Low power, very high performance, and I'll show you some examples. These processors, these systems, the software is all shipping today. And at the end of this presentation, I'll even give you some links to Oracle Cloud Development that you can all just sign up into and you can try out for yourself and experiment and test yourself and see these results. We have SMP scalability, so getting over 400 gigabytes per second in and out of the processor to other processors, and significantly also high I/O bandwidth for PCI adapters. Specifically, it is the world's fastest conventional microprocessor. This was introduced in 2015. It holds a number of world records, CPU intensive throughput, Java, database, ERP. What I'm going to focus on, though, is the left-hand side of this slide, which is on top of that is what we brought by working together, forward with hardware-software co-engineering with our database and our Java teams. So the first thing I'll talk about is security in silicon. And you see the red highlights there is it didn't take a significant amount of die area on the die. That's a die microphotograph. But it's very high performance and very low power. And what we're able to do is put 32 of these cryptographic accelerators on the die. There's a very wide range from SHA to RSA to ECC to AES that is supported by each of those units. They all run independently. As you can see, they can do public key encryption, they can do bulk encryption. You can see the hash functions that are in there. It's extremely comprehensive, and there's actually some competitive comparisons here to some other reasonably contemporary processors. So as examples of what we get out of that from a performance standpoint is here AES 128 CBC, basically 83 gigabytes per second, which is so many times faster than, from a bandwidth standpoint, than what we see on our other processors out there. Same thing for SHA-512. We're basically running about half what the memory bandwidth can provide with those 32 cores. So we're basically looking at order of magnitude improvements versus what we can get on other processors, and this is by just designing custom silicon to perform these functions. Same thing, looking at this on a per core basis, not just on an overall throughput basis. AES CFB, AES 256 there, and SHA-512 again. We're looking at on a core basis 2 times, 7 times. And again, it's by just developing custom silicon and custom functions to perform these operations. What it brings to systems is that the overhead of performing encryption in the data center becomes very small, almost negligible. So today, people hold back from deploying, encryption and all in their data center because the performance overhead is too high. This is an example, if any of you are familiar with a Java multi-tier application database benchmark. This here is spec J Enterprise. And what it is there's application server and a database server. So we encrypted all of the network, you can see at the bottom, and we encrypted all the data on the Oracle database using TDE. And the performance difference when we ran that benchmark was 2%. So the enablement is now basically you want security throughout your data center, throughout your cluster, throughout all your users. Another thing I'll talk about is then query acceleration and capacity in silicon, which is some of our decompression capability. So in the middle of the die there on the ends, we have 4 blocks of hardware accelerators. And you can see, again, not a very large investment in die area, not a large investment in power. But by developing domain-specific hardware, we can actually optimize the hardware for the operations and the functions we're trying to perform. So we have 32 of these analytics pipelines built on the die in those 4 blocks. So it's somewhat like I said, we have a 32-core processor. It's somewhat like adding 32 additional processors. They can actually operate up to 170 billion rows per second. And what they do is not only do they perform operations, but they run concurrently with the other cores on the die. So in this case here, of course, could be running OLTP operations while the analytics accelerators are running low-level operations for data analytics. Another thing they do is, again, this is domain-specific, so they actually are aware of how data is compressed. And they decompress it on the fly and feed it into their pipeline without writing it back to memory. So there's a memory bandwidth savings, there's a power savings with that. So it's almost like adding a number of specialized cores because we're not doing a decompress into memory, pull back out, and then operate on it. So we call that a fused operation. So if you look at the pipeline on that processor, at the very bottom of the block diagram here, there's a set of input queues, and they are sitting on that on-chip network. So they have full access to all of the memory bandwidth, just like any of the cores. Okay. The first step they do is they perform decompression, and then you'll see through the rest of it, they do a set of operations that are programmed to do. Then they reformat the results, and they push the information back out. They run concurrently. They can run asynchronous and concurrent with the cores, or they can run synchronously. And what we did is we developed a user-level fine-grained synchronization primitive to maintain very low overhead between the cores synchronizing with these accelerators. So what we end up with is very high performance at low power. And again, it gets to utilize, it can maximize all of the memory bandwidth of the processor. So the first thing that these accelerators can do is they understand how information is encrypted. We use a combination of dictionary encoding and run length encoding and some specific proprietary compression on top of that. And they recognize that, and the accelerators, each accelerator can sit there and take the stream, decompress it, and operate it specifically on the decompressed information as it's encoded. So, and again, it does that without writing back to memory. So here's a behind the scenes. So again, each of those, what they do is, each of those accelerators at the very top of the block diagram here, they can pull information from another one of the pipelines. So we can actually pipeline from one to another. They can pull the information from an L3 cache that any core had been working on. They can pull the information from DRAM anywhere on the die or anywhere in the SMP. They then perform inline the decompression operation. They take that, they unpack the input, and there's a set of functions that they can perform, whether it's lookups or predicate evaluations or filtering. They then apply the run length on top of that, set up the outputs, and can then pass that on to another pipeline, back into an L3 cache, that's specific to a core, which we can tell it specifically which L3 cache partition to put to send it back to, or into DRAM. And each one of those 32 pipelines before that operation. The operations include scans here, selects, translations, and extracts. So we can do single value range comparisons, each pipeline can. So it's good for searches, searches on range and values, key value pairs, even things beyond SQL. It's also used, and you'll see here, in some XML and JSON processing. We can do selections, filtering functions. We can do lookups to do translations, and of course we can do, and of course the accelerator also does extractions, which is a decompression operation. So it's not only used for the database, which is one of our initial uses for it. We work closely with the Oracle database team. It can actually be used with domain-specific languages. For instance, like Java Streams, that's one example you'll see here, as well as some others. It's accessed, and all those applications can access it coming down to the hardware. The basic library that everyone uses is called libdax. Okay. So the database comes down and uses that. User applications can use that, or they can use a higher level API. And we have two different libvector libraries that provide higher level functions for applications. And this is actually available for use in the Oracle Cloud, which I'll make sure I'll show you we have links to. So the libdax library is a very low-level C interface, and it does all the DAX functions that I talked about. It's thread safe, and it supports multiple different clients. libvector is a higher-level package, performs higher-level functions. It's used many times with Java Streams and Java vectors. So as an example here, if you look at the very low-level performance, all right, if we just compare running the low-level scans, the low-level filters, DAX to running the cores, we took an example here of 15 million lines, and we had 12 different columns of different types of data, but 8, 16, and 32 bits, and you can see the performance advantage between running with the accelerator offload versus running with the cores. And 8-bit operations is significant, and as the elements get wider, the limitation ends up becoming memory bandwidth. But again, we're looking at many times 5, 10, 15 times performance improvement for those operations. And again, at very low power, because there's very small silicon invested in doing that. We've actually integrated this with Java Streams. All right. It's actually out there in the community. The library is available, and a number of different Java Streams functions we're seeing anywhere from 3 to 20 times improvements as well. This is all out there today in the community. It's even being used in other ways. There's other users in the community using it for machine learning, from other types of scans, from other types of streams. And again, they're seeing multiple times performance improvements over using cores alone. So again, they're using the APIs and they're running applications and leveraging the libraries and finding some significant performance improvements. So this is all available in the Silicon Developer Cloud. All right. It's available to universities, researchers, customers, partners. You basically sign up. There's a click-through license agreement. It uses its access through Solaris and Solaris zones. There's APIs. There's use cases. There's code examples. All right. There's pre-built templates. And again, it's a way of trying out and experimenting with your own applications and exploiting the capability we have there. And again, lastly, so this is some more resources here. There's the cloud itself at the bottom, and there's actually a whole bunch of different write-ups on using our libraries and our stream processing in our Spark microprocessors. Okay, thank you.
Yeah, I'll pull this around. I was just wondering, does your crypto support include tamper-resistant root of trust stuff, or is it just purely an accelerator for the algorithms?
The crypto units themselves, all right, root of trust is different from the crypto units themselves.
If you could ask, maybe come out to the aisle, there's a couple of questions. Go ahead, John.
So your mention of machine learning and 4 to 5 times faster in comparison to Broadwell, or in comparison to what?
Oh, this was comparison to running with our cores. They basically ran the applications with our cores, and then they used the library, much like I showed the database applications here. So if we back up, these are all based on them running on those M7, right? And running their code on the cores, right? And then leveraging the libraries and refactoring their code for the libraries and the performance speedups they got. So this is a Spark to Spark improvement.
Okay.
What is the main bus that brings the data in and out of the chip?
I'm sorry?
What is the main bus that?
Oh, the main bus? Okay. So what we have here is, let me get back here. So there's a number of buses, all right? On the right and left-hand side of the buses, these are serial links. They run at, let me think long back, 16 gigabits per second, I believe, no, 12.8, I believe. And all those links run serial, and they're wide. They're so many lanes wide, and they run to these ASICs that are interfaces to our memory DIMMs. And the collection of the SerDes bandwidth there is way over 170 gigabytes per second, but 170 gigabytes per second is the actual data we can pull in and out of DRAMs. From the SMP standpoint, if you look at the top and bottom, there's something called coherence and scalability links. Those run at slightly over 18 gigabits per second per link, and there are you can do the division, but it's over 444 gigabytes per second at the pins of the chip without that's payload. That's without CRC or any link level overheads. So that's the amount of actual information we can move in and out of the chip to other processors. So that's over a whole set of links running at 18 gigabits per second. Then the third set of links are these I/O links that are called ILs. If you can see those connect to an I/O ASIC, and those are also running at 18 gigabits per second, and they can sustain they can actually achieve maximum from a PCI standpoint, 127 gigabytes per second. So there's a significant amount of data that we can push in and out of the processor because we're at a relatively high core count, relatively high thread count.
So the interconnect between the cores, are they like a crossbar or?
The on-chip network, okay. The on-chip network is actually 3 networks. It is a data mesh. The data network is a mesh, all right? It's roughly, if I remember this, half a terabyte per direction. All right. On top of that, it resides a set of request rings. All right. So all requests are sent over a set of rings, and then there's a direct point-to-point response network. So there's actually 3 networks that make up that on-chip network.
Interesting. And the ring, is it a token type of based ring? Or
No, it's not token. It is very low latency. Everything's flying by, and we're snarfing it. Every partition, every one of these partitions here, L3 cache partitions, we're snarfing data off, filtering it, whether we need to see, that partition needs to see it or not, dumping whatever it doesn't need to keep up. So it's extremely low latency. There's no store and forward at all there.
Okay. Thank you.
Thank you. One more question.
Great. So for each of your different encryption algorithms that you're running, do you have dedicated ASICs for each one?
I'm sorry?
Do you have a dedicated ASIC for each one of the encryption algorithms that you're running on the chip?
Oh, okay. So the inside the core, and you can see those blocks. See the size of that block? The cores are roughly, there's basically 4 cores where you see 4 of those small blocks. There's 4 cores in there. So there's actually a set of functional units that are tailored, maybe not specifically to each algorithm, right?
Yep.
And some of them can be shared, I mean, come to be multi-use, right?
Gotcha.
But we actually, what we do is we look across all the algorithms and architect that crypto unit.
Gotcha.
Across all.
So are you doing it in hardware though, or do you have a specialized instruction set that's just dedicated to the crypto
We
algorithm?
have
or-
a specialized instruction set for it.
Gotcha, gotcha. Okay, cool. One last kind of part around the crypto. Do you just work with kind of Oracle, whatever your encryption, key management, or authorization acquisition is, or do you fall under utilize a standard authorization acquisition or key management technology?
I can't answer that. I believe it's the latter. But I think Michael Palmetter will be here. He's probably the right guy to ask.
Cool.
Right.
All right, thank you.
Thanks a lot. All right, let's thank our speaker.